Hey everyone. Today we're on Unit 6, Lesson 5, and we're going to be talking about some applications, mainly like just the way that we can use rational functions to deal with real world situations. Our focus today will be building rational functions, and we did this in a previous unit, and I just want to remind you of some of the basic steps. Okay, so when we're building rational functions, we're going to always write the basic function. And if you remember correctly, that would be like your area function or your surface area or volume, whatever the case may be for the particular shape you're dealing with. Next, you want to find a way to relate your variables. And last, go back and write basic function as one variable. Okay. So the first problem we're going to deal with, United Parcel Service has contracted you to design an open box with a square base that has a volume of 5,000 cubic inches. Express the surface area of the box as a function of x. And like I do with all problems, I'm going to go through and I'm going to highlight what I think is important. Open box, square base, a volume of 5,000 cubic inches, and we're expressing the surface area as a function of x. Okay. So there was a lot of stuff that was important in this problem. First thing I'm going to start with is setting myself up a little picture. This picture does not have to be perfect. Mine is not perfect at all. The square base to us means that this and this are both going to be x units, which makes the height of my box y. So I'll use x's and y's for this example. Now I'm going to go and I'm going to write my surface area formula. And I also want to remind you, when you're writing a surface area formula for this particular situation, we want to remember to go back. This is an open box. So I'm going to need the surface area of just the bottom. That's x squared. And then I need the surface area of each side. So length times width, xy, 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 4xy. And when I look at this situation, I see I have a y value there that I want to write in terms of x. So I have to go back in and I have to find my relationship. My relationship is usually given to me with another formula. For instance, here, they tell me that the volume is 5,000 cubic inches. So I know my volume, which is length times width times height, is 5,000. Length times width times height is x times y. X squared y equals 5,000. I'm going to solve this equation for y. So now I can go ahead and replace the y here with what it's equal to. My surface area formula would be x squared plus 20,000 over x. Now with these formulas, because we're dealing with the rational unit and rational functions, I would like you to express these as a single quotient, meaning we're going to add these together. Some of you can do this in your head, but if you can't, just remember, put this over a 1, and then you could just think, oh, common denominator, I have to multiply by x over x. And my surface area formula as a function of x becomes x cubed plus 20,000 over x. And there you have it. Let's look at another situation. We're always going to kind of follow the same steps. We're going to put in our information and then find out the relationship and replace it. Reynolds Metal Company manufactures aluminum cans in the shape of a cylinder. It's required to have a volume of 400 cubic inches. Express the amount A of material required to make the can as a function of the radius of the cylinder. Okay. So cylinder, that's my shape. It's going to have a volume of 400 cubic inches. I want to express the amount of material as a function of R. There's my cylinder. That's my radius, right? This is R here. So I'm going to first start with the area. Okay, I want the area, the surface area of this. Now the surface area of the cylinder is going to be the bottom and the top. So I have the area of each circle. The area of each circle is pi r squared. Now I have to figure out the wrapping around part. And so if we think about this, might be, if you could see me, might be easy to show you with a piece of paper here. So if I have this piece of paper and if I kind of wrap it in the shape of a cylinder, that looks like a can, right? If I unwrap this, you notice you have a rectangular piece of paper. So if I say, and I unwrap this, I'm going to have, right, a rectangular piece of paper. Now the length of this is going to be the circumference of the circle, 2 pi r, and the height of this is going to be the height of the can. So far, this is the top and the bottom of the can, and 2 pi r h is the outside of the can. My problem here is I have an h and I have to have it all in terms of r. So I go back into my given information and they told me that the volume of this can, okay, and the volume of a cylinder is the area of the base, pi r squared times the height. And this is equal to 400. So if I solve for h, I get that h equals 400 over pi r squared. Now, once again, I could do what I did with every other problem. I'm going to rewrite h with what I got over here. I'm going to make that substitution for h. Area equals 2 pi r squared plus 2 pi r. H is 400 over pi r squared. My pi's are going to cancel, and one of my r's canceled. So my area formula is 2 pi r squared plus 800 over r. And once again, we want to express this as a single quotient. So I put that term over a 1, and then my least common denominator is r, so I just multiply the other term, top and bottom, by r over r. And my area function in terms of r is going to be 2 pi r cubed plus 800 all over r. I wrote it as one single expression. Now, there will be times next year when you want to write it as one expression and you want to leave it separate. So I'm working on this year, you being able to notice that these are equivalent forms. Okay, these both expressions, this guy here and this guy here, both mean the same thing, but we might want to use them one way or the other when we deal with calculus type problems. The last example we're going to do today. A rectangular area adjacent to a river is to be fenced in. The enclosed area is 1,000 square feet. Fencing on the side parallel to the river is $5 per foot, and fencing for the non-parallel sides is $8 per foot. Write a function that describes the cost of the fence. Ooh, this is going to be a doozy. So I've got a rectangular area. It's going to be on a river. So I'm going to have a river. I'm obviously not going to need fencing for that side. The enclosed area is 1,000 feet. Fencing on the side parallel to the river is $5 per foot. Okay, so I'm going to call, I know this is weird, but when I do problems like this, I usually reverse it. I call that Y, and then that would be my X. So this fencing is $5, and this fencing is $8. Write a function that describes the cost. Okay, so first of all, we have to think about what we're starting with. So we're dealing with fencing. We want to know how much it costs. So how much it costs is going to depend on how much you use. So we first have to, my perimeter is going to be 2x plus y. And in order to turn this into 2x plus y, in order to turn this into a cost, I know that my x costs $8 per foot. So this is going to be 2 times 8x plus 5y. Now my issue here is that I have to get rid of that y. So I go back into my original information, the enclosed area. Okay, that word is important. We've never really done it this way before. Now this time, my area, which is length times width, right, is going to be 1,000. So once again, here's how I relate my variables. Y is 1,000 over x. And I'm going to take what I got for y here and put that guy right there. So my cost function, 16x plus 5 times 1,000 over x. And if we want to express this as a single quotient, okay, now we can just, hopefully you guys can see this in your head by now. This is just going to be 16x squared plus 5,000 over x. If not, all I did was I put this over a 1 and then I multiplied by x over x. And this would be your cost function. Okay. So those were just a couple of, real simple building functions that we may see in the future with our rational functions. Okay. Thanks. See you soon.